This video is sponsored by Brilliant. What does it mean to have a vacuum? An empty space which is void of all atoms and matter. But what about energy? What if I told you that vacuums contain enough energy that they cause space-time itself to expand? Because as we'll see, space can never truly be empty. And while both general relativity and quantum field theory predict and allow for an expanding universe or vacuum energy, neither provides an adequate description for what's behind such an expansion. Quantum field theory, or QFT, is one of the most accurate tools we have for describing interactions on the subatomic scale. It is so accurate that it's able to predict the energies of particle decays to 1 part in a million. However, though it suggests a mechanism for vacuum energy, the resulting magnitude disagrees with observation by over 120 orders of magnitude. This has famously become known as the worst prediction in all of physics. In this case, how has such an otherwise successful model led to high disparity with experiment? Let's begin by considering the vacuum in a quantum mechanical paradigm. Although vacuums do not appear to contain any physical particles, as by definition they must be void of such, the quantum fields which inhabit the universe persist everywhere, even throughout vacuums. In quantum field theory, every particle and subsequent interaction is modelled as an oscillation or localized excitation in a corresponding quantum field. As an example, you can imagine giving a number to every point in 4D spacetime. The higher that number, the more energy from a quantum field is present at that point in space and time. We perceive these localized excitations in quantum fields as particles, and although the fields for different particles are distinct, the fundamental forces allow for different decays and interactions between them. That's quite a simplified picture, but the key message behind it is what will help us to understand what is really going on in vacuums. Even with nothing else present, these quantum fields fluctuate on tiny scales. This can be attributed to Heisenberg uncertainty in energy and time, whereby due to the lack of a common eigenbasis of energy and time operators, there is an uncertainty principle associated with their observables. That's just a fancy way of saying that the mathematics behind quantum mechanics causes there to be a fundamental lack of information when it comes to measuring both energy and time. In the universe, this manifests in the following way. During a short time interval delta t, there can be an associated Heisenberg uncertainty energy delta E, provided that the following relation is obeyed. This energy appears in the form of particle-antiparticle pairs, which always seek to annihilate each other once delta t has passed. Applied to a vacuum, this means that in very short time intervals, particle-antiparticle pairs can and do form within the vacuum. Since these particles are destined to annihilate, they're coined virtual particles, existing for only a brief window and then disappearing forever. This isn't uncommon either, with many pairs forming all over the vacuum. Because of this, even the truest vacuums in quantum mechanics can never be completely void of particles at any instant. This also leads on to vacuum energy and the worst prediction in all of physics. Using quantum field theory, you can work out the amount of energy stored per volume of vacuum. This means that empty space itself should have an intrinsic energy density associated with it. The formation of virtual particles in space would provide a negative pressure in vacuums. This sounds an awful lot like an idea from Cosmology, where observations of distant supernovae explosions show that spacetime itself appears to be expanding. You can imagine the universe as the surface of a balloon which is being inflated. Every point moves away from every other point. This expansion only occurs in voids in deep space, which themselves are almost complete vacuums. What's more is that the expansion is accelerating. Hence it is being driven by negative pressure, which must be caused by the presence of vacuum energy, which inherently occupies the empty space. One way to work out the energy density associated with the vacuum energy in cosmology is using light curve data from standard candle supernovae and seeing how their brightness changes with distance in space. As it turns out, the measured value for vacuum energy from cosmology is so much smaller than that predicted by quantum field theory, so much so it's become known as the worst prediction in all of physics, with the measured value turning out to be over 120 orders of magnitude smaller than the theoretical prediction from quantum field theory. How can such an otherwise accurate and dependable theory predict a value which is so far off experiment it's beyond laughable? It could be to do with what's thought to be physically causing the vacuum energy. Cosmology doesn't give much insight into this. Instead, it merely indicates that the bulk property of empty space is negative pressure, and it is likely in the form of cosmological constant or vacuum energy. This tells us nothing about what's happening on quantum scales. Conversely, the idea that vacuum energy is caused by virtual particles coming in and out of existence due to fluctuations in quantum fields may not necessarily be correct. Not only does this prediction give us a value that's monumentally incorrect, but how can we be sure that virtual particles even exist? This is a topic of much debate between particle physicists. Sure, virtual particles seem to make sense, and the mathematics of quantum field theory allow for them and even predict them, which ultimately is how many particle decay routes happen, but no one has ever detected them directly. This could simply be because, by definition, virtual particles must annihilate almost immediately in order to conserve energy and momentum. Hence, it is impossible to measure a single virtual particle. In a similar way, it is impossible to create energy out of nothing. An important point regarding the energy-time uncertainty principle, which we relied on so heavily to predict the existence of virtual particles, is that it must still obey the law of energy conservation. For example, imagine a particle decaying into 3 other particles, and each of these decaying into more particles. Provided that at the beginning and at the end of the entire decay, energy is conserved, what goes on in the middle can be heavily influenced by Heisenberg uncertainty and virtual particles. For example, you wouldn't know if an electron from a specific decay was what was measured in experiment, or if instead that particular electron annihilated with a positron from a virtual pair, and it was then the leftover electron that was detected. Energy is conserved either way, and we cannot know. Thus, directly observing virtual particles is a big ask. Nonetheless, attempts have been made to observe them indirectly, one of which being the Casimir effect. The main idea here being a phenomenon where bringing 2 conductive plates extremely close to each other, of the order of nanometers, will cause them to eventually feel an attractive force and be pulled together shut. To explain the reason for this effect in terms of virtual particles, we must first consider the wave-particle duality in quantum mechanics. On sub-nanometer scales, matter becomes wave-like in nature, with seemingly solid particles being able to diffract through slits, like waves. This motivates the idea of a wave function in describing the properties of particles on quantum scales. A popular example in introductory quantum mechanics courses is that of a particle confined in a box. The laws of quantum mechanics only allow for wave functions with integer numbers of wavelengths to fit and exist in the box. The particle then has a linear superposition of all these wave functions before measurement. While I am quickly running through this example, the key point is that particles exist as waves, and you can think of it as the wavelength of the allowed wave is determined also by the confining length or size of the box. Not any size wave can fit in the box. Now let's go back to our 2 conductive plates. As they get closer together, less and less of the virtual particle waves are able to fit in the space between the plates. However, outside the plates, where the space is much larger, many more waves are able to fit. This difference between inside and outside the plates then causes them to experience a small force pushing them together, as more waves are incident from the outside, pushing them in, than there are inside pushing out. Therefore, the Casimir effect is seen by some physicists as indirect proof of the existence of virtual particles. But note I said some physicists see this. That is because an alternate explanation in the form of van der Waals forces can also be applied here to explain the Casimir effect. Van der Waals forces are microscopic forces between miniature electric dipoles which form due to electrons and ions in solids. At very close range, these dipoles are able to attract each other, imparting an incredibly small force, just strong enough to pull the plates together. The idea of van der Waals forces goes back even before quantum mechanics, and is well documented as existing. Interestingly, this is how geckos are able to walk upside down and stick to surfaces. Their feet are adapted to employ the van der Waals attraction between dipoles in their feet and on the surface. Today, there is still an open debate with papers from both sides attempting to explain the Casimir effect, so we currently cannot say definitively whether it is caused by virtual particles or van der Waals forces. Both explanations seem to work. Nevertheless, virtual particles also lead to Hawking radiation. Here, one of the virtual particles from the pair forms in a black hole, and the other just outside the event horizon. The one inside cannot escape, obviously, and so the other particle never annihilates and is released from the black hole as Hawking radiation. This is a mechanism for the evaporation of black holes over time, and is ultimately possible through the existence of virtual particles. Sadly, however, Hawking radiation has not been verified experimentally, and so remains theoretical at present. Could it be possible that the major discrepancies between the vacuum energy predicted in cosmology and quantum field theory be down to the inexistence of virtual particles? If so, why does including their existence make everything else in quantum field theory seem to work well, predicting the results of experiments with profound accuracy? Or maybe virtual particles do exist, but it's something else entirely which causes vacuum energy and the expansion of the universe. If you want to learn more about quantum mechanics, cosmology, or any of the math and physics I presented here in a free and easy way, then check out Brilliant, the sponsor of this video. Brilliant is an interactive learning platform which specialises in math, science and computing. There's courses for everything, even the concepts in this video. For that, I'd say check out their Quantum Objects course to gain a deeper understanding. It covers many things like the need for quantum mechanics in modern physics, as well as how we handle observable quantities and particles and waves in the quantum paradigm, all of which I've referenced and applied here in this video. I personally love Brilliant, as each lesson contains many visual aspects and diagrams instead of just lines of text, which I think makes learning fun and intuitive, if you couldn't already tell from my channel. Brilliant also helps you to learn by doing, with each lesson quizzing you every step of the way to help your understanding. There's a lot more than just quantum mechanics on Brilliant, with new courses added every month, so there's always something for you to be working on. Don't worry about the complexity of the courses either, as no matter your ability, Brilliant will help you learn valuable STEM knowledge, all the way from basic to advanced courses. It has everything. You can try out Brilliant today free for 30 days using my link, brilliant.org/OV Astronomy, and the first 200 of you that do so will also get a 20% off an annual plan, only through my URL. I'll also put this link in the video description. Using Brilliant is the best way to learn new skills in science, math and computer science, so I'm so glad I could share them with all of you. Thanks again to Brilliant for sponsoring. Remember to check out my link in the description to try them out for free. See you next time.